All right, guys. So chapter 2 is we're going to talk about matter and energy. So you may be asking yourself, what is matter and energy? So these are so matter and energy. So we want to be able to distinguish, what is matter, what composes matter, and energy. How are they related? So basically, let's talk about matter. So matter is here. Matter, everything that has mass is matter. All right. So my iPhone, water, soil on the ground, buildings, anything that has mass is composed of matter. So there's three types of matter that we need to take into consideration: macroscopic. So here's macroscopic. Um, so macroscopic basically means it's matter on a scale that is observable by the human eye. For example, those things I just mentioned, we can see them with our naked eye. So they are called macroscopic um, uh, type of matter. Okay, so we go a little bit bottom now. Microscopic is matter on a level too small. Oh, sorry, not too small. It's basically matter on a level. Let me go back. Let me backtrack. Sorry about that. So matter on a scale that is observable by a classical microscope. So classical microscope. So like anything of like biological nature, like a skin cell, maybe an egg cell, a virus, a virus, a bacterium. So anything that we can see under a microscope or things you would encounter like when you're observing cells or specimens in biology, for example, plant cell, stuff like that. So that's microscopic. So think microscopic, like discernible, but only by the use of an instrument such as a microscope. And macroscopic is things you can see with your naked eye. And then we come to the last classification is particulate. So a particulate is basically anything, so matter on a level too small to be observed. Sorry, I just typed the same thing. To be observed. Too long to be observed by a human. Matter on a level too small to be observed with the human eye or microscope. Okay. Sorry, that looks. I'm very bad at this handwriting. I need to do it better. Okay, so that is our classifications of matter. So now a question would be like, oh, what type of matter is termed macroscopic? And I'll give you a list of options, and you just pick the one that you can know for sure you can see with your eye. So example of our particulate classification of matter is, things we can't see normally, like electrons, atoms, nuclei of atoms. So stuff we cannot see. We can't see light particles or photons. So stuff like that. Okay. So the thing with particulate matter, we need models. So for particulate matter, we need models to help us understand how these things can look like in the real world. Okay, so that is learn the classes of matter. Okay, so I talked about a few examples already. So let's just go back and list them. So example here is say like examples, sheet of paper, or something like a ring, like a wedding ring. Microscopic, like I said, some examples were plant cell, animal cell, or a bacterial cell. And then so it turns out like a virus, sometimes they're so small they're hard to see. So let me backtrack on that. So a virus is actually kind of like on the boundaries between microscopic and particulate. But for some more examples on particulate, let's go here. So some examples are protein molecule, water molecule, and atom, the size of an atom. So those are all examples of particulate classes of matter. Okay. Moving on. So when we talk about models, so in chemistry, we need to use models to represent these structures. So let's talk about that. So the two type of models that we use are, a model is a representation of something, right? Of something. And what we use models of atoms and molecules to help us communicate what these things look like. So the two most common ones, models, which are based on experimental data. So we don't just come up with this on the fly. We extrapolate what the data tells us and put that into meaningful depictions for atoms and molecules. So the most common ones are ball and stick. So for example, so ball and stick is where I have a 3D representation of a molecule that uses balls to represent atoms, and we use sticks to represent electron pairs. So I'll show you what I mean by that. So, for example, bond sigma of, for example, methane, which is CH4, would look like this. So we use a central atom right here. That'll be my carbon. And then we're going to use sticks to represent pairs of electrons that are bonded to the other hydrogen atoms. So let's use the red for hydrogen. Okay, sorry. So right here, the black sphere is carbon, and then the red sphere is hydrogen. All right, so that's ball and stick. So that's a common way to represent these molecules. We can also use a second type of representation, which is also pretty common. So another representation is called space filling. So of the types that we usually encounter when we teach chemistry is usually the ball and stick, but space filling is also important to represent, like how compact the molecules can be. So space filling, so basically you don't have bonds anymore. You don't have sticks. You just have spheres that are kind of bunched together, and I'll show you what I mean. So let's see. So we still use, so for example, we use spheres of different colors to represent the atoms. And so we do show the outer boundaries for the space filling, but we no longer show the bonds or the electron pairs for the sticks. So I'll draw you an example with the same idea. So again, here is my carbon atom. Sorry, it zoomed out on me. So here's the central carbon atom, right, that we showed before. And now, instead of drawing lines or sticks, we're going to draw the hydrogen atoms kind of showing an overlap in the boundary on the sphere. So that'll be one carbon or one hydrogen atom. Here's the second one. And then the third ones are kind of in the back right here, but they're kind of hard to see in this 3D image. So, but essentially, that's the same picture as this one up here above it, except we don't show the bonds as electron pairs. So those are two ways that in the internet molecules are represented, atoms and molecules. So that is the picture here. One thing I want to know is that the boundaries represent 3D character. So those boundaries now are kind of what associate the bonding interactions between the two atoms. Okay, so don't worry too much about what the bonds are or how to draw these. Just know that these are how we represent represent matter in terms of chemical compounds and molecules. Okay. So next, so you might be wondering, oh, what does C and H mean, right? So in our models, they're called chemical symbols, right? So chemical symbols right here, chemical symbols. So chemical symbols. So for example, H is an hydrogen atom. And then oxygen is an oxygen atom. Okay. So how we read formulas, for example, we have H2O. How would we read that? Well, we would say it has 2 hydrogen atoms and 1 oxygen atom. And guys, if my voice goes out or the internet uses my mic, I'm sorry. That's why I'm writing it on the iPad so you guys can see what I'm kind of talking about. So if it ever cuts out, let me know, and I'll try to fix my spotty internet connection. Okay, so we have 2 hydrogen atoms and 1 oxygen atom. So now if we go back up, we can see our CH4 molecule. So CH4 is methane, or what we call natural gas, and that's buried deep within the earth. So for methane, it's CH4, so we have 1 carbon atom and 4 hydrogen atoms. So that's how you read this compound. But don't worry about how the molecules are connected or the atoms are connected. We don't need to worry ourselves too much about that right now. Okay. So those are chemical symbols. That's the basic of chemical symbols. Let's go down to states of matter. Okay, so now we're going to talk about states of matter. So states of matter, hopefully you guys know all of them. It's the most common ones. So the states of matter that we talk about are solid, liquid, and gas. There's technically a 4th one, but we're not going to talk about that. So the differences in the states of matter is we can talk about them by using the kinetic molecular theory. So let's talk about that states of matter. So here we go. Kinetic molecular theory. And what that says is all matter consists of extremely small, or sorry, let's say tiny particles that are in constant motion. So here's kind of some mnemonics to help you break down the definition. Kinetic it means motion. For example, like the popular term telekinesis, that means you can affect movement at a distance. So here kinetic means motion or movement. Okay. So molecular, it comes from the word molecule. So molecular is just the adjective of molecule. So we're referring to the movement of small molecular particles, and that gives rise to our physical states of matter. So the thing is, so molecules are attracted to each other. Right? So molecules are attracted to each other, and those attractions are what give rise to our states of matter. And at higher temperatures, so the thing about the attraction is that what we want to say is the speed So the speed of the particles is faster at higher temperatures and lower and slower at lower temperatures. For example, if you take the solid state, right? The solid state, the particles are not really moving because the solid stays in place. But once you get to a liquid, you see that you can move the liquid, right? And the particles are moving together uniformly. And once you get a gas, you see the gas quickly rises and like disperses. That means the particles are going to be moving really fast. And there's no longer really any attractions because they're just flying all over the place. So that's why when you boil water, you melt water, right? It's really cold. But once you warm up the temperature, it goes to liquid at 0 degrees, above 0 degrees. Then once it reaches 100 under normal atmospheric conditions, it'll turn from a liquid into a gas. So the higher temperature you get to, the faster the particles will start to move. Okay. Okay, let's talk about the states of the matter. So we have, hold on, let me just check the time. So, okay, we have about 30 minutes. Hold on. So, let's talk about the states of matter. So in a gas, so gas right here, we have a gas. So in the gas, particles are moving, so particles are moving fast and far apart. So in this case, we overcome the attractive forces. So they're no longer being tightly bound into like uniform substance, right? That's why gases, when you see gases, they quickly, try to evaporate up into the air. So here we overcome the attractive forces. All right, how about liquid? So let's use blue for liquid for water. So in a liquid, molecules are in constant contact with each other. So the molecules, they touch one another. They touch each other. And they freely move amongst themselves, right? Because as you like pour water, it comes uniformly out as like a puddle of liquid, right? It's one flowing, like river or like a flow, and it's not like individual particles. You can distinguish them, right? They're all uniform as a single unit of matter. So they touch each other and move freely moving. And freely move among themselves, okay? Oh, terrible at writing with this pencil. Okay, so now we have a solid. So in the solid state, molecules vibrate in fixed positions. What I mean by that is molecules. So the molecules, they're not like fixed. Well, what I mean by that is that the molecules, they don't want to stay fixed. So when you start heating them, they'll vibrate. And once those vibrates reach a certain temperature, have enough energy to break free and that's when a physical state change occurs. So molecules vibrate in fixed positions. That's why when you see like solid ice, the molecules are frozen and they don't move. So like when you try to move a solid, it'll stay in completely in the same position and the same shape. Whereas in a liquid, it will always conform to the container that you have the liquid in. And gases are that way too. So you can contain gases too, unless you open it up to the atmosphere and they all evaporate out. But water, liquids, they conform to the shape of their container and they have a variable volume. Whereas solids, they don't take the shape of their container and they have their own volume, fixed volume. And that's why that's kind of related to the fixed positions that solids have, because they're not freely moving amongst themselves, right? They're in stable, well, not stable, but fixed positions. So there's two types of solids we want to maybe talk about. So we have crystalline. So crystalline means the solids. They're solids where the molecules are arranged in a definite pattern. So the arrangement is kind of ordered and fixed. Well, not fixed, but not fixed. It's like a formal arrangement. A very specific, definite, formal arrangement of how the molecules are packed, like A, B, C, etc. Something like that. And the next is called amorphous solid. So amorphous is the solid which lacks pattern in its particle arrangement. Oh, sorry, wrong pen. Okay, so those are two different kinds of solids. Liquids and gases, there's only one form of liquid. I mean, there can be two forms, right? Because the molecules are no longer or the particles are no longer fixed. Okay, so let's make a graph here. So here is gas, liquid, and solid. So let's talk about these. So I'm going to draw this schematic, but it's in the slides, so you can always reference them too. So gas, we have the particles freely moving. For example, here's my particles of gas. They're freely moving. All right, so here the gas particles are moving. Liquid, let's draw our beaker here. Our liquid, we have a water level, right? So in that level, the water molecules are close contact with each other and they can move freely within the liquid. So that is what we talk about when we're talking about freely moving and having close contact with each other. Solid, on the other hand, looks like a fixed ice cube, and all the particles are fixed into that shape, taking a specific volume. Okay, so let's go over the shape. So shape of a gas. Well, the shape of a gas, we call it variable. So what we mean by variable is that it takes on the size of its container. or same as a closed container, right? It will be the same as a closed container, right? So what do we mean by same as a closed container? So if we were to if we were to put a lid on top of that gas beaker, the volume, it will occupy that volume of the container because it'll be bouncing off the walls and it will occupy that space. Liquid is variable as well. So whatever you put in the liquid in, it will assume the shape of its container. So it'll be the same. God damn. Sorry. I mean, darn, I can't seem to write well. Same as the bottom. Same as the bottom of container. There's a difference between gas and liquid because liquid, they can only occupy by gravity what's at the bottom, whereas gases, they're always moving about in a closed container, so they'll occupy all that space. So for solids, they are constant, a constant shape, and it's rigid and fixed. So it will not change no matter what container you put it in. It'll always assume its own shape. It'll never conform to the walls of the vessel or container. Okay, so let's talk about volume next. So volume is, so the volume of a gas is variable, right? So depending on what vessel you use, right? It can it assumes it could be the same as it can be the same as a closed container, or it can be variable as when you open the container it will just fly away, right? So the volume it occupies is always change, is it can be variable and it's not necessarily consistent. Liquids, on the other hand, once you put them in a container or a space, right, they occupy the same volume no matter what. No matter if you open the container or you close it, it'll, assuming that evaporation doesn't occur, it'll always assume the same same volume. So this one is constant. And of course, for solids, the shape determines its volume, so it'll never change. So that is also constant. Okay, so let's talk about, this is just basically a summary of all our ideas here. So let's talk about particle movement. So particle movement for gas. So the movement is very random for gases, right? Random. And it's independent of every other particle. So it's random, so the movement of each particle can go anywhere in the container. Random, anywhere in closed container. Let's talk about liquids. So the movement is for a liquid is very limited, right? So it's independent beneath the surface. So it's so let's say it's kind of beneath the surface. Beneath surface, the movement's independent of each other. Independent. Beneath the surface, you have independent movement, so it can go anywhere, but it's limited to the volume of the container. And so it's independent, but limited to volume of liquid, and bottom of container. So the liquid can move freely underneath the surface of the liquid, anywhere between, independently of the particles. But that movement is determined by the liquid itself, how much volume it occupies, and the shape of the container, or where it can go on parts of the container. Okay. Excuse me. Excuse me. Sorry about that. Okay. Lastly, let's talk about solids. So solids, they don't move really. They just vibrate in fixed positions. So they are vibrating in fixed positions. So they're vibrating in fixed positions, so they don't really move at all. Okay, lastly, let's talk about, whoops, sorry. Let's talk about particle spacing. So particle spacing in gases, gases are flying, they're quickly rises and flying fast about. So they are very, very far apart. What this means is that there are virtually particle to particle interactions are negligible. Particle interactions are negligible. So because the gases are moving very fast, right? The gas particles are moving very fast. And liquids, they're close. So they're close together. So close together. And in this case, what holds the liquid together are those particle interactions. So we say that the particle interactions are important. Because these interactions are called intermolecular forces, and they are what hold the states of matter and gives them their identity. So like water is free flowing, water vapor is like inhaling mist, and it disperses, like once it's in your face, it goes away into the atmosphere. And then solid ice, well, the molecules don't move independently of each other. They're moving as a single unit, like an ice cube or like a block of something, a block of ice, block of liquid, something like that. So it's very rigid. Okay, and lastly, for solid, they're close as well. So it's kind of the same thing as a liquid. Because if the solid moves as a single like piece of matter, that means its interactions has an important part in keeping it together as a whole. So in this case, particle interactions are very important here too. So particle interactions important. Okay, so that is states of matter in a nutshell. Okay, so we have a little bit more time. We're just going to keep going until time is up. Okay, let's talk about what like states of matter. What do we mean by like physical properties and chemical properties or chemical changes? Let's talk about that, because that's a hallmark of chemistry, is noticing whether something's a physical change or chemical change. And I will most likely test you on this sort of distinction, so I will keep in mind what I say here. Okay, so let's talk about properties and changes. So physical properties, what do we mean by physical properties? Okay, physical properties, they are characteristics So there are characteristics that can be observed or, oh, sorry, not or, and measured without altering the identity of the substance. For example, when I go from solid to liquid to vapor of water, the physical appearance of the water will change, but the identity does not change. So like if I take an ice cube and melt it and drink it, it'll still taste like water, and it won't taste like something different, and will have a different effect on me, right? So we say that's a physical change. The identity of the substance is the same, but the physical characteristic of it has changed. Okay? So without altering the identity of the substance. So physical change, I kind of went over that, but let's recap. So physical change would be changes that occur in the form of a substance without changing its identity, without changing its chemical identity. So those what we talked about were, for example, solid ice melts to liquid water. So that is an example of a physical change, right? Our water has been converted from a solid to a liquid. Okay, so now let's talk about chemical change. So chemical change. So chemical change, what do you mean by that? So it's just the opposite. The chemical identity of a substance is destroyed, or basically you turn it into something different entirely, and a new substance forms. So chemical identity, so the chemical identity of a substance is destroyed. It's destroyed, and a new substance forms. So this is known as a chemical reaction, also known as a chemical reaction. So that's the heart of all chemistry, the chemical reactions, and that is what happens for a chemical change. And chemical properties, what we describe chemical properties as is, so chemical properties, so they are, all the chemical changes possible for a substance. So they refer to like, change in color, difference in smell, the evolution of gas or heat usually indicates a chemical change, but don't get that confused with like evaporation of like a liquid to a gas. That's not a chemical change. That's a physical change. So there's those kind of those can be confusing as well. So let's see. All right, a few more minutes. Let's talk about like one last thing, and we'll be good. Okay. So I talked about physical change, like when we go in from a solid liquid to a gas. So, for example, if we evaporate water, right, we see our water molecules in this beaker, and here it's a solid, right? So let's just redraw that. So say I have a beaker here, and here's my solid ice. So here, and if I applied some heat to it, I eventually turn that water into liquid, right? Into a liquid here. So here's a solid, liquid, gas. And once I applied more heat to the beaker, now my water, there's nothing here, and my water has basically evaporated, right? So here is an example of a physical change. So this is called a physical change. So physical change. So I'm applying heat, but I'm converting it to the different physical state, but still maintaining my water molecule. So here this is solid H2O, liquid H2O, and then gas H2O. And where the gas molecules will be floating about, going away from the flask and into the air. Okay. See what else we got. So chemical change will be okay. So for the last minute or so, sorry, for the last thing we'll talk about are chemical changes. So here's one example. Here's a chemical change. So if you ever burned sugar, you know it turns into like caramel. I actually didn't know this until recently, but if you burn sugar, you're actually converting it to a different substance, and it's this sugary. Eventually, you know, it mixes into this caramelized caramel first. So basically, you have. Sorry, let's just write this out. Sucrose. So sucrose is my reactant. That's what I start with. So now if I apply heat, so if I apply heat, and what this arrow means, it means just changes to. So he changes to. Well, let's just ignore that. So once I apply heat, so let's put heat plus sucrose, and that arrow signifies that my sucrose will turn into carbon plus water, and plus water, and these are my products. So this signifies a chemical change because I have sucrose on one side, but now I'm converting it to carbon and water. And so there's a picture of this in the slides, but basically what it shows is that you have here is sucrose. Once you start heating it, it turns brown. So right here you have a layer of liquid, and then here's a second layer that's kind of colored. So it turns brown. It caramelizes, and turns brown. So that's basically how you make caramel, that sticky substance that's kind of delectable and tastes good. And that starts forming. So if you heat it to a higher temperature, even higher temperatures, you're going to cause further decomposition. So that further decomposition looks like this. And basically you have all black, let's just make this a little bit different color. So let's say this red stuff is the caramel stuff, right? So eventually this will all turn into a completely different substance. Let's name it blue. So you'll have this completely different substance as you heat longer, and that's and basically that this black stuff is carbon, and then what's evaporating out of the pan is water. So burning any carbon compound will get you back to its elemental form, which is pure carbon or soot, or those pure black carbon. So this will cause further. So it'll cause charring, which is that black carbon residue, and then release water vapor. So this is an example of water reaction. You started with sugar, which looks brown or like pale white, a pale tan, and you get it slowly turning brown, and then eventually turns black, and this black guck, which is called charring or soot, or that's called well, we call it when it's pure carbon charring, and it usually has this black color to it. Okay, guys, that's the end of this lecture. I hope I had your attention the whole time. Hopefully this kind of method works. I will post this lecture tomorrow at 12:10. It'll be available at 12:10 on Canvas. Feel free to watch it, and if there's any problems, let me know. So, well, this has been fun. Hopefully I get to talk to some of you, maybe in office hours. But if there's any questions, don't hesitate to ask. Okay. All right, guys. See you later.